Section 13.7 is called acceleration of the rotor slip. And what we want to see is, okay, so in 13.6, we looked at this situation, where, the motor's at rest or the rotor's not turning, it's locked rotor conditions. We looked at the environment that created when we applied the three phases of electricity, magnetic field, voltages induced, currents flow, interaction of magnetic fields, torque developed, all that sort of thing. Now, what happens internal to this motor once the rotor starts to turn? All right, so I was thinking, what could we use to demonstrate this better? And I really think this slide works best for this explanation. Okay, so here's that slide that we looked at, when we initially started thinking about this idea of how this induction motor worked. And again, what I want you to think about this, I want you to think about this ladder as being the rotor, okay? And of course, that it's, the ends are rolled in on each other to create a cylinder, actually a squirrel cage looking thing, right? And so, so what we ended up with, was this thing here, right? And so the effects that are occurring, I think, are easier seen by looking at this ladder that's laid out flat, okay? And again, everything is sort of based on this equation where the voltage induced is equal to the flux density times the length of the bar that's subjected to the magnetic field times the speed. The relative speed is actually more about what we should be talking about. And the speed in terms of the speed in relation to the moving magnetic field in relation to the bars, okay? Now, initially at startup, this is at 0. So whatever this speed is just the speed of the magnetic field. When this starts to move with it, there's a difference, right? So we got the one speed of the magnetic field minus the speed of the ladder once it starts to move. But anyway, that's, where we're going with this. And that's the basis and thing we'll look at when we go through this explanation in 13.7. So as soon as the rotor's released from lock rotor, it rapidly accelerates in the direction of the rotating field. Okay, so in this case, we're saying that the force that's causing it, the direction of that is, it's indicated here, right? So this ladder is going to move in that direction, and it's being drug along with it, and this causes both the value, this voltage, and the value and the frequency of the induced voltage to decrease because the rotor bars are cut more slowly. Okay, so this is how fast are those bars being cut? Well, once it starts to move, once the ladder, the rotor, starts to move, they're not being cut as fast as they were when it was standing still. The rotor current, very large at first, slowly decreases as the motor picks up speed, right? So if this relative speed goes down, this voltage is going to go down. If the voltage goes down, the current's going to go down too. The speed will continue to increase, but it will never quite catch up with the revolving field. If it did catch up and it was at the same speed, if it did get to this synchronous speed of the magnetic field, then the bars wouldn't be cut anymore. Okay, so you have to have that action of the flux cutting the bars. If that no longer occurs, then this goes to 0, right? And all bets are off at that point. So under the conditions that we talked about, like that would be 0 and no more voltage developed. So what you have to have in an induction motor is the rotor speed, the ladder here in this example, will always be slightly less than the speed of the magnetic field. You have to have that relative speed in terms of cutting the bars. And if you lose that, then that goes to 0 and it no longer exists anymore. Okay? So at no load, the percentage difference in the speed between the rotor and the slip the rotor and the field is called slip. Okay, so slip is the difference between synchronous speed of the magnetic field and the actual speed of the rotor. And that defines slip. And that's going to be something that we can build from and create our second equation.